Oui.
Super. Très bien. D'accord. Okay, so we can start. So welcome everybody to the webinar of today. The speaker of today is Antoine Dazin, and he's going to talk about active flow control for axial compressors, surge margin improvement. So as usual, I introduce the speaker very briefly, and then I leave him the floor. So Professor Antoine Dazin obtained his PhD at the University of Lille in 2003, after a postdoc at CNES in between 2004 and 2006. He has been an associate professor between 2006 to 2016, and he's currently a full professor since 2016 at Arts et Métiers campus of Lille. He's in charge of the research thematic rotating flows at LMFL, and his research activities are focusing on the internal flow behavior of pumps and compressors operating far from their design points. He is currently the scientific coordinator of a European project on flow control in turbomachinery, ACONIT, and some point .eu if you want to check the project. And he has been involved in many collaborative projects with the special and aeronautical industry. So it's a great pleasure for me to introduce Antoine Dazin today. So Antoine, I stop sharing my screen. You can share yours and you can start.
Yes, thanks a lot, Francesco, for the introduction. Okay, perfect. Okay, so thank you very much. Before starting, I want to thank I would say the co-author of this presentation. So all my colleagues of the team in rotating flows here at LMFL who have contributed to the works I will introduce. And also, and a special thanks to Pierre-Joseph, because I think I have stolen about 3/4 of the slides you will see in a minute from presentation he did in the past. Special thanks also to some other colleagues from Onera and here from École Centrale at LMFL who contribute also to some part of this work concerning PIV for most of them and numerical simulation for some of them. Yes.
Antoine, I stop you just a second. We see your full screen, but it's in like in personal presentation mode. So maybe you can put it totally full screen. It's probably what you see that we see as well.
Okay.
So,
yes, I'm sure I can do this. Okay. Now you cannot see anything.
Yes. Yeah.
Okay, I will stop the sharing and restart it.
Yes.
Okay. Like this. And now, no.
Yeah, that's perfect. And that's still like we see your. You can start now presentation mode, I think, because we see the PowerPoint. Top left, you have the presentation button, I think.
Yes. But this is what I did. No, this is not good.
You may.
Okay. Ah. No, what time? This.
No, we still see.
But
you can. Yeah, now it's perfect.
Oh, okay, good. Thank you. I don't know why. Okay. Okay. Okay, so to give you some words about the motivation of this work, I will start with two slides about the evolution of aeronautic engine. So this one is concerning the past. So you can see that compared to the first engine, so basically in the 50s. Okay, what between this is working, yeah? Yeah, okay. Okay, sorry again. So compared to the first engine, so basically in the 50s, the engines that are on our planes today, the engine manufacturer managed to reduce the specific consumption of the engine of about 1/2. Now, if we look to the past, and I have just copy-paste a web page from the ACARE association, and what they plan is that for 2050, to reduce the CO2 emission to 0. So the paths that have been done in, I don't know, something than 70 years to go to 1 to 0.5, they want to do it in less than 30 years to arrive to the 0 CO2 emission. So this is obviously a great challenge. So let's have a look to how an aeronautical engine operates. So basically, it is sucking air from the atmosphere. This air is compressed in the compressor, then sent to the combustion chamber where the fuel is burned, and the hot gas, which have a lot of energy, pressure and temperature, are then going through turbines where they are expanded and then ejected in the nozzle of the engine, and this is what is producing the thrust. This is the basic concept. And now we have more complicated engine, but the basic concept is here. The operation of this part, this engine in terms of thermodynamic is given by the Brighton or Joule cycle in France. You have here, so this is the ideal one. This means that we consider that the compression and expansion in compressor and turbine are completely isentropic, which is not true, but it is just to give you the main idea of the motivation of this work. The efficiency of this cycle is directly linked with the pressure ratio done by the compressor. So if you increase the pressure ratio of the compressor, you will increase the efficiency of the engine. Now we will focus on the compressor. So actually, what we have in engine is not one compressor; it's a series of compressor, and each stage of compressor is composed, like we can see on the picture on the right, of one rotor and one stator with non-rotating. So we have a series of rotating blades, and then a series of fixed blade, which are fixed vanes, which are called outlet guide vanes. So if we want to increase the pressure ratio, basically we have two solutions. Either increase the number of stages of the compressor, but then we will increase the weight, and this is obviously a problem for something we want to see fly, and or to increase the pressure ratio per stage, and we will see that this is also a problem because we want to increase the pressure difference in a component which is naturally submitted to an adverse pressure gradient, because its role is to increase pressure, and the flow is likely to become unstable. So to understand this, I'm showing what we call the performance map of a compressor. So you have different performance curve at different speed of the compressor. On the x-axis, you have the mass flow rate going through the compressor, and on the y-axis, what is of interest for us to increase the efficiency of the engine, that is the pressure ratio. So if we focus on one performance curve at one given rotating velocity, so first, let's see what is happening if the compressor is operating at what we call the design operating point. So that is the operating point, so velocity and flow rate for which the compressor has been designed. Then here in red, you have the velocity coming into the compressor, so seen in the absolute frame, but the velocity seen by the blade of the compressor are seen in the moving frame. So what the blade is seeing is the relative velocity. And at the design point, the machine is designed so that this relative velocity arrives on the blade with zero incidence. And the compressor operates in perfect condition. So now if we move to the left to go close to the maximum pressure ratio of the machine, once again, having in mind the possibility to increase the efficiency of the engine, then the flow rate is decreased, so the velocity in the absolute frame is decreased, and you can see that the incidence in the relative frame is changing, and we arrive at condition where there is a risk of stall. Okay, and stall in compressors arise, and actually there are two different unstable phenomena which could arise close to this maximum pressure ratio. They are called stall and surge. So I will try to explain you what they consist in. So the first phenomenon is called rotating stall. So this is basic concept is a stall because of a problem of incidence, like presented in the previous slide. But I will show you a video of simulations that was done, I don't know, something like 10 or 12 years ago at Onera on the inception of stall in a compressor. And okay, I will try it like this. Okay. So I will, I've even lost my mouse, so. Okay. Sorry for this, I will try to show you. Okay. Okay, I think you can see it in the presentation mode, but I will be able to show you the presentation and then switch back to okay. Can you see the video, Francesco?
Yes.
Okay, good. So here you have the rotor, and here you have the stator vane. So the flow is coming from the left to the right, and the flow rate is decreased slowly, and you can see the stall of some of the blade, and it is called rotating stall because you can see that all the whole blade are not stalled. There is only a part of the compressor which is stalled, a part of the blade channels which are stalled. I put it again, and now if you look carefully to one blade which is starting to stall, and you follow this blade, you will see that the flow will reattach. For example, if you follow this one, it is starting to stall. Well, okay, not good. This one, it is starting to stall and then reattaching. So the stalled stall is in a way rotating around the diffuser at a velocity which is different from the rotating velocity of the machine. Okay, so now I have to go back to the presentation mode, and this is quite a challenge for me. Okay, so what are you seeing, Francesco? Tell me that it is good.
I see the like the PowerPoint
Okay.
version so far.
Okay, so this is not good. This is what I did. Okay, and now?
That's screen is refreshing. Just a second. I think it's good. Yeah, it's good. It's good.
Okay, and now if we switch to the other unstable phenomena, which is more dramatic and which is usually triggered by a stall. This is called surge, and surge is a strong axial oscillation affected the whole system. And you can see two examples, one on the picture and here on the video of an engine which is stalling, and you can see that this is obviously not very good for all the mechanical parts composing the engine. Coming back to the characteristic curve, so you have here the surge limit for the stall limit of the compressor, and the consequences are so dramatic that the user of compressors in many applications, including aeronautical engine, are taking a safety margin, which is called the surge margin. And so they deprive them of the possibility to use all this part of the characteristic curve and all the good pressure ratio and good efficiency part of the curve. So this lead to bigger and heavier engine. This is what I said, and to give you some numbers. If there is a paper reference here who said that if you divide by you increase the surge margin by 2 or deprive, or if you have a factor 2 on the surge margin, you can remove up to 2 stages on the 10th stage of the compressor, and so have a lighter engine. So the idea of what we will do and what I will present in the work is to push the stability limit in the left in order to be able to reach this region of high pressure ratio. So that is increasing the surge margin. So to the metric associated to this surge margin is based on the distance between the nominal point, so the design point of the compressor, and the operating point where it is stalling, and it is based on the flow rate and pressure ratio at the nominal point and at the stall point. And then if you find a solution to push the stall limit by any solution, you have an improved point where the machine will stall. You can calculate a new surge margin with this improvement of the stall margin, and the stall margin improvement is basically the difference between these two values divided by the surge margin, the original value of the surge margin, and it is given as a percentage. Okay, so this is what we will use to characterize our system in the rest of the presentation. Okay, so all the rest of the results you will see are based on let's say simplified test case. This is an axial compressor, single stage axial compressor test bench we have at LMFL. So here in Lille, it is composed of 30 blades for the starter, 40 blades for the rotor. It is relatively low speed as we are usually operating it at 3,200 RPM. And to give you an idea, the rotor diameter is about 1/2 meter to have a possible an idea of the size of this compressor. So our problem is not when the compressor is stalled. Our problem is to prevent the stall to act before the arising of stall. So now I will give you some words about what we call the precursors of the stall. So how the compressor is going to stall condition. And if you look at the literature, there are two different paths for a compressor to go to stall condition. The first one is called modal stall inception, and the second one is called spike. Well, this is an historic. These are historic definition because were based on the first measurements done on this phenomena using just pressure sensors on the casing of the compressor. And they have seen that depending on the geometry of the compressor, you can have some cases where you have some low amplitude, long wavelength oscillation during a great number of rotor revolution, and then they increase in amplitude and going to stall. So this is what is called modal stall inception. These phenomena are well predicted by a linear stability theory, and it is this is a unstable phenomena between the machine and the system, and this is linked to a change in the slope of the performance curve. So the normal slope of the performance curve of compressor is negative. This is the normal operating points, and this kind of precursors are occurring if you have positive slope or close to zero slope of the positive or just slightly positive slope. This is not the most common way to go to stall. The most common one is called spike, because what was observed on a pressure sensor is just a small spike in the pressure signals, and then it was going very rapidly in only a few revolutions to completely stall conditions. This occurs in the region where the characteristic curve has a negative slope. And it is not predicted by a small perturbation theory. This one is the most common in modern aero compressors, so we will focus on this one. To show you how we can characterize it on our compressor, so the one you have seen before. What we did is to put a series of pressure sensors all around the circumference of the rotor, so from 1 to 9, and you can see the trace of the pressure of each pressure signals from 1 to 9 as the function of time on this graph. So this is not the time is scaled by the rotation velocity, so you can see the flow revolution, the number of flow revolution on the x-axis. Here you can see the first spike or spikes on the first compressor, and they start rotating around the compressor. Okay. And then here you have a completely stalled condition, and you have a transition of, I don't know, I will say 2 revolutions of the compressor. So this is very quick. Huh? You have in mind that it is rotating at several thousand revolutions per minute. And here in 2 revolutions, you have the first spike and the completely stalled revolution. So you go from this operating point, not stalled, to this one completely stalled in, I don't know, 0.2 seconds, something like this. Okay, so what is the cause of this spike transition? Actually, from recent works, especially from the Whittle lab in the UK, we know that this is associated to the what we call the tip leakage flow. So this is the flow which is created in the gap between the rotor and the casing. And when you are going to, if you increase the incidence at the tip of the rotor, well, depending on the size of the gap, you have 2 different phenomena. One associated to a corner-like separation of the flow, the other one of an interaction between the tip leakage flow with the next blade. But in both cases, this is occurring at casing. This leads to a flow separation close to casing, which enlarge and then propagate around the rotor. And more specifically, the Poulan in 2015 have shown that the spike is linked to this is a kind of footprint of tornado-like vortex, which is creating at the tip of the blade and which is attached to the casing. And when this tornado-like vortex is passing in front of the sensor, you have this spike. So this drives us to the idea of our control system is to try to stabilize this region close to the gap of the compressor. And then we arrive to this control system where we have some series of 40 actuators all around the circumference of the rotor. They are located close, a little bit upstream to the leading edge of the rotor, and they are blowing here. So you can see the shape. So we are using the Coanda effect to keep the flow attached to the wall to really act in the gap here between the rotor and the stator. And we had the possibility to rotate the nozzle of the actuator to change the velocity of the angle of blowing. The maximum velocity we can reach is around 300 meters per second. That is about 3 times the blade velocity. And we are able to inject about 3%, so it's a very small, 3% of the main flow rate you have in the machine. So this is a small quantity of flow, but at high velocity. We have the possibility to use them on pulsed operation up to 500 Hertz, but the results I will show you will focus on the continuous blowing data we have obtained. This is a picture of the characterization of the flow. Here you have the nozzle of the actuator, and this was obtained by a hot wire measurement performed at Onera Lille. So here you can see view of the jet here in a meridional plane, and you can see that what we aimed is to have a flow really attached to the wall. Well, we managed to do it quite well. Here, you can see the location of where would be the the blade in the application in the compressor. Okay, so I will now go to the results we have obtained with after this very long introduction, to go to the results we have obtained with this system, trying to answer to this three question: does it work first? If not, I will stop the presentation. Then, does it work efficiently? And we will speak about energy balance, and then go back to some physics to try to understand how does it work. So does it work? The answer is yes. So here you have the baseline. It's just one example. So you have the baseline. So the characteristic curve. So the characteristic curve without control, and here we are switching on the control system, and you can see that we are increasing the pressure ratio of the compressor, and we are shifting the stall limit on the what is this, on the left of the figure. And then we did what scientists are doing when they do not understand anything, is they are doing parametrical study. So we have changed the injected mass flow, the number of injector used, the blowing angle, and we also tried pulsed and continuous blowing, but once again I will show you only results of continuous blowing. So concerning the flow angle, well, once again, I'm showing you what kind of velocity triangle. So this is the velocity of the jet. But once again, the jet is created in the fixed frame, but the blade are rotating. So the blade is seeing this velocity in the relative frame with an angle written beta, and what we have seen is that we have the best results in terms of SMI when the flow angle is close to the stagger angle of the compressor, which is quite logical. So we at tip we are deloading the blade, and we are then stabilizing the flow by avoiding having too strong leakage flow. Thank you. Then how efficient is the system? So I will not show you all the results with the modification of velocity, number of injectors, and injected mass flow rate. I will just give you some an idea of the results. And by answering this, when you increase the velocity, the number of injectors, the injected mass flow rate, everything is linked. And in a way, you are changing the quantity of mass or momentum you are putting in the flow. So I will just try to answer to this question: what is happening if you blow more? So the first thing we can say that the more you blow, the more you shift the stall limit on the left. So this is good. This is what we want, because we are more and more counteracting what is happening in the gap of in the tip gap region. Now, concerning the pressure rise of the compressor, it depends. In some cases, you can increase the pressure rise of the compressor because you are decreasing the intensity of the tip leakage flow and the losses associated to this tip leakage flow. And then this is good. But in some cases, if you blow too much, actually, the pressure rise of the compressor can decrease because first you are sending a very high velocity jet in a flow, not a Gaussian flow, but a flow at a lower velocity. And a great part of this dynamic energy is dissipated before being able to act on the blade or even after. And you are also increasing the friction because of these high velocities. So to try to evaluate these two effects, you have used two different metrics, which are kind of natural. The first one is the one I have already presented. So this is the SMI, the surge margin improvement, which is basically the difference between the stall limit in non-control and control operation. And the second one, it's a difference of power provided to the fluid by the compressor without or with control. And we have plotted a figure like this with the power balance on the right and the SMI on the horizontal axis and SMI on the y-axis. And obviously, we are targeting this region with a positive power balance. So we are giving more energy to the fluid than in the baseline condition. And on the y-axis, you have the SMI, the initial goal of this study. Here are some of the results we have obtained. So the different curves are for different number of injectors. So this is the injector are by pairs. So you are going from 5 pairs to 20 pairs of injectors. And each line of this figure should be read like this. You cannot see anything like this. So when you are going from the bottom to the top and then rotating on the left, you are increasing the mass flow injected by injectors in the the mass flow you are injected with the control system compared to the mass flow rate of the compressor. So this is a percentage. And this was exactly what I was saying. If you blow too much, then you will decrease the power balance. So then, so to answer to the question, is the system efficient? Yes, there are some situations like here where you have a positive power balance. So thanks to our control system, we are improving the operation of the performance of the compressor, and we are improving quite a lot the SMI. And then we have other maybe interesting point in some situations. So imagine that you need or you know that there is a high risk of surge of your engine. You can use this kind of point where you are spending energy compared to normal operation, but you are pushing a little bit more the stall limit, and you can avoid the stall phenomena by using the control system. Okay, now a few results about how the flow behave when the control system is activated. So we have said that we are acting at the casing, so we will start to some results obtained at the casing of the machine. So just to explain you the results you will see on the next slide, we have used a series of sensors located on different axial position on the casing, and you will see some graph with the value of the pressure and color level. On the y-axis, you have the axial position, so from leading gauge, trailing gauge of the rotor. And on the x-axis, you will have time, but it is corresponding more or less to the theta position because the rotor is moving during the experiment. So what we will compare, these are two results obtained like this. The first one with name A is the last operating point before stall in the baseline. This is without control. So we are here in the performance curve. And what we can see is what we can identify is this small spots of low pressure, which actually are corresponding to these tornado-like vortices which are attached to the flow. And we are in a situation where they will at one moment lead the flow to detachment and then stall of the blades. Now, if you blow, so you are at the same flow rate, the same operating point, but you have activated the blowing system, you can see that they have completely disappeared. And if you look carefully, the blue zone corresponding to the size of the tip leakage flow is first smaller, and it looks more steady, as if you look at the different blade passage, you have more or less always the same shape of this blue part, whereas here you can see that this is probably more fluctuating. So this works in the sense that this is obviously stabilizing the flow. I will show you also some very recent results. These are runs calculation performed by Clémence Roinou, which is actually doing his PhD in the lab. So these are steady runs calculation. I'm showing you similar results. So A is a baseline, B is with control. And you can see a velocity map at 96%, 96% of the blade height, so very close to the casing. And here you can see once again the footprint of the tip leakage flow in the baseline, and you can see that it is very close to be able to interact with the leading edge of the following blade. Whereas when the active flow control system is activated, then you have the tip leakage flow which stays nearly stick to the blade and is not likely to interact and perturb the flow in the following blade. So at casing, it is working quite well. And now I will show you what is happening in the rest of the span of the compressor. Oh no, sorry, not yet. And now you will see similar pictures of the results obtained with the pressure sensors at the casing, but this time we'll compare this A point, so the close to the stall limit without control, and close to the stall limit with control. The time scale on the axis is different, and here we were just looking to some 7 revolutions. In this case, we are looking to a transient from normal operation to stall operation. So we have 40 sensor revolution. Without control, we can identify, as usual, I would say, this oscillation, this strong oscillation of the flow, this peak. So this is typically a spike, and then we have this transient to stall very quick. In the case of blowing, what you can use, yes, you can identify here. This is clearly seen here. Some spots of dark red value of pressure, which are corresponding to small oscillation of the flow. And this means that in this case, we have, and we cannot identify the spike just before stall. So we have this modal oscillation, which is corresponding to the other path to go to stall condition. And if you look at the performance curve in control operation, you can see, so it's quite small because it's very at the end, but when you are controlling the flow, just before stall, you have the slope of the curve, which is becoming positive. So you are in the condition to obtain, according to linear stability theory, condition in which modal stall should appear. Okay, so now what is happening in the rest of the compressor? So we did some PIV experiment, thanks to the help of this guy, for example, who broke one mirror, but who also helped us a lot to perform these measurements. So we did well, quite classical PIV. So this means standard 2D 2C PIV at low frequency. The light sheet was created by using an endoscope, which is installed a little bit upstream from the rotor. So here you can see you have the blade of the rotor, the blade of the stator. Here you can see the endoscope entering into the machine and the camera used for the experiment, and even the target is installed in the blade channel. We did some experiments at 3 different heights. So one as close as possible to the hub. So it was, I think you cannot read it, 79% of the blade height. So this is as close that we were able to do, but actually we are not we are not in the region where we can see the tip leakage flow. We are under this region. We have a second, we have made a second plane at mid height of the machine, and a last one close to the hub. The results you will see, these are average velocity map only at different location, different operating point. And what is plotted is the projection of the velocity in our plane, but we will plot the relative velocity, so the velocity in the rotating frame. Okay. So to begin, these are results obtained without control at the design or nominal operating point of the machine. This is on the left, one map obtained close to the tip of the blade, and on the right you have the map obtained on the hub of the blade. So I've seen that in the remote audience we have some specialists of compressors, and they won't be surprised because you have this classical decrease of the velocity from the inlet to the outlet of the compressor, which is one of the cause of the increase of pressure in the machine. So this is quite normal results. At this operating point, now I'm showing you some result with control, which is of no interest at this operating point because there is no risk of stall, but this is just to show you what is happening. First, please take care that here you can see the leading edge without control, and we were not able to see it in the control PIV measurements because you have the injectors, which is located in this region, and it was masking the optical access to the flow. So we are losing the region of the flow close to, unfortunately, close to the leading edge of the blades. the flow is not so changed. Well, this is normal because we are blowing at the tip and we are looking at the flow under the blowing location. The only thing we have seen is a slight increase of the velocity, probably due to a redistribution of the flow induced by a kind of blockage created by the jet at the casing of the machine. Now, if you are looking to the results obtained at the last stable operating point without control, so just before classical stall, you can see whenever you are that there is not so much which is happening in the flow. You have here close to the suction side of the blade a region of low velocity which could correspond to a slight detachment from mid-chord to the trailing edge of the machine, but not much. And once again, this is quite normal because we know that this compressor in normal operation is stalling because phenomena occurring at tip, and all our PIV measurements are obtained under this tip leakage region. So we are looking to a region where nothing interesting happens during the transient to stall in normal operation. Now, if you look at the results obtained at the last stable operating point, but with control, so this operating point, what you can see is that the flow is completely detached on the region close to the tip, and is also partially detached close to the hub. So this means that on the whole span of the compressor, you have a great detached region, and the flow is blocked in the main part of the passage. But in spite of this, the flow managed to find a region where it can go through the machine, and is still and the compressor, in spite, this is crazy, in spite of this big detachment, is still operating quite normally. This detachment is due to the fact that we allow the compressor to go to lower value of the flow rate. So we are increasing and increasing more and more the incidence on the flow, leading to more and more detachment in the machine. So this is allowed by the compressor. And then just out, if you just throttle a little bit the machine, then you will go to stall with modal oscillation. And that's it. We are close to the end. So I hope that I have convinced you that we have some solid proof of the concept of controlling the flow with jet blowing. So we are at a low TRL, but this is an introduction to the next slide. The system is efficient in the sense that we have many operating conditions where the power balance is positive, and we have at least begin to understand some of the aspect of the flow physics. So to try to summarize the kind of scenario of what is happening in the flow when we are activating the control, here you can see a sketch of a performance curve with the flow rate on the x-axis and the pressure ratio on the y-axis, and you have the baseline characteristic curve, so the one without control. So, sorry. Okay, so when you are blowing at the tip, you are stabilizing the tip gap, and so you are increasing the pressure rise of the compressor if you blow not too much, and so you have a shift on the up of the compressor curve, and you are delaying the stall because you are stabilizing this zone of the flow. So you are moving the you can go to lower value of the flow rate of the compressor. This was the target. Then, if you continue to go to lower and lower flow rate, you are increasing the incidence on the whole span of the compressor, which is not possible in normal operation without control. And we have seen that the channels are partially blocked. This increases the losses in the more and more the losses in the compressor. And then as the losses are increasing, this is affecting the performance curve of the compressor, which is becoming positive. And now we have completely killed the possibility to have some spike at the tip, but we have reached some conditions for which modal oscillation are possible, and the compressor is going to stall with modal oscillation, and we cannot do anything because this is not happening at tip. This is happening on the rest of the compressor and on the system actually. Okay, next steps. So we are working at the moment on a European Clean Sky project, and the objective is to increase the TRL of such kind of system. So in the consortium, we are with our usual partner on this subject, Onera. We have also small company in Rhône-Alpes region, CTEC, specialized in piezo actuators component, which is designing actuators which are able to support vibratory high temperature conditions that can be encountered in a real engine. And the idea is to test such actuators in a real engine located in Munich at the University of the Bundeswehr. So the final test should be in 1 year. And in parallel, we are still working in the lab on the subject. So we have ongoing the PhD of Clémence Ranou, co-supervised by Julien Marty from Onera, on the effect of the tip gap on the efficiency of such systems. And we have a second PhD. I'm co-supervising with the chairman of this session, Francesco, and one colleague from Onera Paris, Jean-Christophe Loiseau, about the optimization of such system and precursor detection by machine learning. And that's it. Thank you.
Thank you very much, Antoine, for this very interesting talk. So I would say we can open the floor for questions. Maybe we can give the priority to the people in the room. Is there any question there?
Yes.
You say that the mass flow rate of the control is up to 3%, and you say that it's not much. So what is acceptable, and do you think that in a realistic flow control, the one would be compatible with aeronautics, we can reach this amount of 3%?
Okay. So shall I repeat the question, Francesco?
I think it was clear. I've heard the question in any case, so I think it was okay.
Okay, so the question is very relevant. I have not so clear answer. I can give you some elements. The first 3% is what we can do when we are blowing very fast, but we have seen that this is not the most effective blowing condition. So the most effective are around 2%, but this is still not so far from 3. I would say that the most important thing is the power balance for the compressor, or the energy which we are injected is well used. And this was one of the challenge of the project, because the first results we have obtained during the first PhD were just about the SMI, and we have one industrial partner, French motorist, not to cite him. One of the engineer was always asking us, okay, your system is nice, but does it pay its place? And this question of the quantity of mass flow rate is related, I think, to the quantity of energy we are using. And actually, to be completely honest, we are a little bit cheating by showing the power balance results, because we are doing the power balance only on the compressor. And this is true that we have some cases where we have a positive budget of our system. But in a real engine, this high pressure, which is used to feed our actuators, should come from somewhere, and it will come from downstream of the compressor. And then we will use some energy, and we have to take it into account probably, but I don't know how to do it, to have a real convincing, in the industrial point of view, energy budget analysis.
Antoine, I have a comment about this, which can be kind of a follow-up to the question of Jean-Philippe. So when you say, okay, we need to include the energy of the used actually for the flow control, if we combine this with the first slide you had, in which you talked about the reduction of weight, due to the reduction of CO2 related to also the reduced number of stage for compressors. Actually, what I think is that we should also include this as one of the factors that has an impact on the compressor, so on the net gain of using a control, because you said before, like, if you move the stall margin, you can reduce the weight. If you reduce the weight, then you gain also in that sense, right?
Yes. I will let you answer the other question also. Yes, this is true, but at this stage, we have to convince, if we want to go to industrialization of the concept, we have to convince that this system offers a very good quality, because the aeronautical world is always very reluctant to make some modification, because they then have to qualify everything, and it is very complicated. So we have to prove that this is as efficient as possible.
Yeah, so in this case, basically the optimization process would consist of two phases, showing that this flow control is an optimal control, or somehow a very proper solution for current architectures. And then next step, it can unlock other architectures which are currently unavailable, basically.
Yeah. Yes.
Okay. Okay, cool. Are there other questions in the room?
Well, you said this tornado vortex takes some time to restore.
Yes.
Do you understand why it takes some time?
Well, sometimes it's.
What is the time?
Typically it's some. I will give you a turbo machinery time is I don't know, 2 revolutions of the rotor.
Yeah, that's what I thought. Is that long? Is that not long?
well, I will have some difficulty to answer to this question. Long compared to what? Okay, the compressor has to do 2 revolutions, but this small tornado vortex should enlarge sufficiently to occupy the whole, well, a great part of the channel, and then propagate to the neighbors. Because if you have just one channel which is told, this is not so much a problem for the compressor, it will continue to operate correctly. So it has to propagate to the neighbors to arrive to a completely developed stall. So and then in terms of time, we have to counteract. This is very quick, because in a real application, this is less than 1 second. So you have to detect the phenomenon and then to do something. Actually, what the monitoring system are doing in real engine is switching off the gas if they detect that there is a risk of stall condition. And what we want to do is to replace this by a tip blowing system. Okay, and so we will have some less than 1 second to switch it on. So it's short. Okay.
The shape of the blades doesn't have any one.
There are some, yes, sure, but what the designer, well, I'm not an expert in design, but you are not, so I can tell you what I want. But what they are trying to do is to increase the work per stage, and so they are increasing more and more the pressure difference between the both sides of the blade, and they are increasing the magnitude of the tip leakage machine, and so they are likely to increase this phenomenon rather than decreasing it. Actually, there are other solutions. They are called casing treatment. There are some attempts to manufacture some grooves on the casing to in a way balance the pressure between the pressure side and the suction side at tip, and this is working well also. The main drawback is this is creating losses, and it is affecting the performance of the machine at a normal condition, what we have not with our system. Okay, any other question in the room?
Yeah, very quick one. You said that there are 10 stages, compressor stages. Do they behave all the same? So the control could be the same on all the stages, or you have to parameterize with respect to the...
Well, in principle, it should work. Usually in a series of compressor stage, the stalling is starting from one specific stage. So we could think that this is most interesting to control this one and to put the control system at the level of this stage. But then probably if you control one stage, this is another stage which will start to stall. And in the end, if we are using this, probably we will have to put it on several stages. The other problem is that we need some high pressure. So high pressure difference between the bleeding and the main flow. And this will be easiest to do it on the low pressure stages, lowest, let's say, lower pressure stages, because we have possibility to use the higher pressure stages to bleed the system. If we are arriving to the last stage, we will be able just to use the pressure rise provided by one stage to feed the control system. Okay. So, yeah.
Is there some are there some other questions in the room?
I don't think so.
Okay, so maybe we can ask if there are participants who would like to ask a questions from far. So just feel free to unmute your mic and ask a question if you have any. At the moment, I don't see any questions, so maybe I can take the chance to ask you one. Staying on this slide, you have basically two different, like in the figure which shows the two regimes, like the blue and the red regime for the tip leakage jet dominated vortex and the casing corner separation dominated. Is there any reference in literature that shows how control, not necessarily active, also passive flow control, affects these two regimes? I mean, are they both controlled more or less by the same mechanism, or are they both somehow, are we capable of manipulating both of them in the same way, or they react differently? Because on one, on like the red part is really a sharp pressure gradient which separates a vortex at the very tip, and in the other case there is a separation bubble which is much more massive, it seems.
Okay, so there are not answer in literature as far as I know, but we're working on it. Actually, first, the actual design of the SEM2 compressor, well, the usual design, I would say, is just at the limit, because the tip gap we have is 0.5% of the cord, so 0.6. So we are very close to this limit, and this is effective. So you will say you are not answering the question because we are just in between the two. Okay. The second point is that our tip gap is very small compared to real machines, and in aeronautical application we have a tip gap from 1% to 2%, so we are more likely to be in this region. And at the moment, we have one of our PhD students, Clémence, who is doing some experiments with the compressor with an increased tip gap. And what we have seen is that the system is even more efficient when we are increasing the tip gap. So when we are clearly in this regime, our system is working better than where we are close to the limit. So why is it so? I cannot answer at the moment. Probably the response is more complicated than just about these two physics. There is probably also something to investigate about the thickness of our jet compared to the size of the tip gap. But we have to work on it.
Okay, thanks. Let's see once again if there is someone who would like to ask a question. Just once again, if you want to ask a question, feel free to unmute your mic. Huh? No, this doesn't seem to be the case. If there is no one in the room who would like to ask a question, then I think we can close the seminar. So thank you a lot, Antoine, for the presentation. It was very interesting, and as you saw, it triggered a number of questions, which is always good. So I invite the audience and to thank our speaker of today. So thank you, Antoine.
And thank you, Francesco, for forcing me to prepare. Thank you all.
Have a good evening to everyone.